Hello, welcome to the second video on the components down a slope. In the last video we were talking about how this angle theta here is the same as alpha, and also the meaning of what the components of this weight are, what the meaning is of the component that goes down the slope and how it's the same as this side here, and the component that goes into the slope here and how it's the same as this one here, although that's not so relevant. So in this one we only got to sort of prove that alpha and theta were the same angle, and I wanted to talk a little bit about the expression for these two components and what they're normally used for. So this being the hypotenuse, or the biggest force that's interacting here, it's two components which are always worked out at right angles like that to each other. They both add up to this one here. So the way we normally break up components, if we take this whole length to be the length of the whole weight, then this force that goes in that direction would be the component of the weight down the slope, and this component there that goes into the slope, that would be the weight perpendicular to slope. Okay, and these two are very useful for different things. But if this force goes in that direction here, right, and this force here goes in that direction, then when we add the two forces heads to tail, they give us the real force that we have, the W, right? So what we're doing here is really the opposite process. We start with the weight and we decompose it into these two forces in order to make it more useful for us in terms of calculating what will actually happen with this block, whether it will slide down, how much the friction is, and things like that. So as we've seen, I'm going to break it down, but we've seen very often that when we have a hypotenuse like this and we have an angle here, alpha, which I'm now going to substitute and go ahead, and since we've proved it, I can be bold and just change it and write down theta, since we've just proved that theta down there will be the same as this guy. So if this is my W here, then this is my adjacent to my angle, and that's my opposite to my angle. So my adjacent from SOHCAHTOA, whenever I'm dealing with an adjacent and a hypotenuse, these two, I always want to use the C, which is the cut, and that's the cos function. So the cos function multiplied by my hypotenuse is W, then W times cos of the angle will give me how much of that force is going along this direction. And similarly with this one, if this is the opposite, then I'm dealing with opposite and, well, sorry, not opposite and adjacent, that we're dealing with opposite and the hypotenuse, which they give us. So opposite and hypotenuse is these two guys, so I'm going to be using the sine function. So the one the component here that I'm interested in that goes down the slope would be not delete that, would be W sine theta, right? So that's how much of this W is going in that direction there. The W cos theta is how much is going in this direction here, right? So why is that useful? Why do we want to split this W into these weird directions? Well, this one hopefully makes sense because that's parallel to this, parallel to that, right? And a force here in space like that, that's a force. It's the same if this force has an effect, you know, on an object. It's the same if we draw that force there than this one, right? If they are the same size and the same direction, both forces, they're the same force. So just because we've calculated it down here, this component, it doesn't mean that it's having an effect down here. It's actually being applied here in the center of mass. So to see that, you could just complete the rectangle and see that this size of this rectangle is the same of this side, is going to be the same as this side here. It's just we're calculating it down here so we don't mess the diagram up there. Okay, so How is all of this useful? Well, if this is W cos theta and that's W sine theta, then we can use these two for a few different ideas. First of all, the W sine theta, which is the force that's acting on this slope down the slope, on this block down the slope. If this is the slope and that's the block, then if I want to know how much force, how much of this weight is going on in that direction, then it's the same as, and this is theta, then that's also theta, and therefore this here it will be W sine of theta. And if W sine it because it's the opposite, as we just set up here, and if the weight is say 100 newtons, then I can just say, well, out of those 100 newtons, 100, and then let's say that theta is 30 degrees, then out of those 100 newtons I know that 100 times sine of 30 degrees is how much it's the component of the weight down the slope. That's how much this force will be here. So if I do it in the calculator, whatever that comes out to be, 100 sine 30, 100 times sine of 30, that's 50. Yeah, because sine 30 is a half. I forgot about that. So then the force that goes in that direction would be 50 newtons. So then I know how much is going down, and if there's no friction, for example, then I would know that I can use F equals ma to find out what the acceleration of the object is. So if I know the mass, which is 100 newtons divided by 9.8, whatever that comes out to be, let's say that the gravitational acceleration is 10 instead of 9.8, then the mass would be 10 kilos. It's an approximation. And then if the only force acting is those 50 newtons, then I know that my resultant force 50 is equal to 10 kilos times A. So then A would be 5 meters per second squared. And I could calculate all sorts of things, like what the velocity is going to be down here after it travels for 100 meters, or after it travels for 10 seconds, using my Suvat equations and things like that. So that would be really handy and useful. And what else? What else could we use these for? Well, another type of situation we could get is where they tell us that the block is not moving. Okay, so imagine that they tell us that imagine that they tell us that the block is not moving. So they could tell us if the block is being held by friction, or is not moving, or being held by frictional forces. In other words, if the slope is not smooth forces, they could tell us find the magnitude of the friction. Okay, and imagine that they told us that m is 50 kilos and theta is equal to 30 degrees. I use 30 because then makes things easier when we calculate things. And so find the friction. So that's easy. We've got the slope, I've got my object here, and I've got my real weight there, and this is how much of the weight is going to be going down the slope, and this is the friction. I'm going to do that in a different color. The friction is going up, that's friction, force of friction, that's the weight down the slope, and this is W, right? That's W, and the angle is here. This angle there is 30 degrees, they told us. The mass is, what did they say, 50 kilos? Yeah, 50 kilos. 50 kilos. So the whole W is going to be, W is equal to mg, that's easy to calculate, that's 50 kilos times 9.8, but let's take 10 in order to, for simplicity. If it's 10, then the weight of that object is going to be 500 newtons, right? If the weight is 500 newtons, we split this up into components as we've done before always, and it's always the case that this angle is the same as that one, so that's also 30. And so the component down the slope, which is this one, is the same as this guy down here, is gonna be the whole weight times the sine, because it's the opposite side of 30. Sine 30 is a half, so if the whole weight is 500, the component of the wave down the slope is going to be equal to 250. 500 times half, so 250 newtons is the component of the weight that wants to go down the slope. And if it's not moving, if the friction is holding it there, then the two forces must be at least equal. So therefore we can say that the force of friction is equal to the weight, so to the component of the weight on the slope, which is equal to 250 newtons. Okay, so that would be a really quick way of doing it. Hopefully by seeing it like that done quickly, you can see that it's not that tricky. Sorry about the messiness, but I'm just trying to get through some ideas quite in a non-boring sort of way. And what other questions can we be asked? Well, this is more for the mechanics people. You don't need to do this so much in physics, but they can give us the coefficient of friction of the slope, and they can say something like, let's see, I'm gonna write out the example and then we can save some time. I'm just gonna pause this. Okay, there it is, as by magic. So we have a slope and they tell us the coefficient of friction is 0.5. The coefficient of friction is basically used in this way. The coefficient of friction multiplied by the reaction force. The reaction force is this guy here, how much the floor is pushing up on the object. That's the reaction, and that's exactly as much as the object is pushing down on the floor by Newton's third law. So if you get mu and you multiply it by r, then you get your frictional force. So they could tell us, say, hey, if mu is 0.5, then tell me if this is gonna move, if it's gonna slide up or down. Well, let's see. For that we need to compare the force that goes in this direction. We need to compare this force with the friction, and now we can calculate how much the friction will be. So if the weight here they tell us is 200 newtons, then how much of that weight is going into the ground? We're very interested in that. So that's W times cos, because it's the adjacent. This one into the floor is always going to be cos of 20. That's going to be 200 times cos of 20. So 200 times cos of 20 is the force of this block on the floor. That's the same as the reaction going up, because the block is not moving in this direction at all. So therefore we can calculate their friction. I'm going to do that just quick. Well, the reaction, or W cos 20, comes out to be 188 newtons approximately, and that multiplied by mu, which is 0.5, will give us our friction, which is half of that, and if I divide this by 2 I get 94 newtons roughly. 94 newtons is the force of friction. So I know that that's how much this force is, around 94 newtons, and now I need to compare it with this one down the slope. So this one down here, it's always W sine, because it's the opposite. So that's 200 sine of 20, and that comes out to be 68.4. So the component of the weight down the slope is equal to 68 newtons approximately, and the friction going up is 94 newtons, because this coefficient of friction, to be honest, is quite big. It's normally between 0 and 1, and 0.5 is quite a sticky surface. So 68 is going down the slope and 94 is going up, so therefore this guy won't slide down. It will stay there until somebody comes and pushes it with their hand, or the thing gets heavier somehow, or I don't know, and then it will start sliding down when the force down the slope equals this 94 newton. So hopefully that makes sense. Whenever you have a question dealing with friction and coefficients of friction, then you're very interested in this component, because the more you press on the floor, the more the reaction force from the floor on the block will be, and therefore when you do your calculation of the coefficient of friction times the reaction, you will get a bigger friction. And then you normally need to compare that with the force going down the slope to see whether it will move or not. Okay, so hopefully that makes sense. If you don't do mechanics, if you just do physics, then this last part is not so important for you, but this part that we did before is very, very important, that you know how to split this up into the component down the slope, which is always going to be the weight times the sine of the angle. And you can compare that with the frictional forces, and you can calculate work done and think work done by friction as it moves down, or work done by the weight as it moves down, and things like that. So hopefully that helps, and yeah, see you in the next video.